Distilled water at 25 degrees centigrade is characterized by sigma equals to 1.7 into 10 power minus 4 mole per meter and epsilon is equals to 78 epsilon naught at a frequency of 3 gigahertz. Its loss tangent tan delta is, the options are given like this. Option A 1.3 into 10 power minus 5, option B 1.3 into 10 power minus 3, option C 1.3 into 10 power minus 4 divided by 78, and option D is 1.3 into 10 power minus 5 divided by 78 epsilon naught. Here for a distilled water he asked the loss tangent. Before that, just recollect what is loss tangent. Loss tangent is nothing but the tan of some angle which describes how much loss is there. Whenever the loss tangent is more, there will be more loss. Whenever the loss tangent is less, there will be very less loss. To characterize any material, we can use this loss tangent, and the loss tangent is given as tan delta, which is equals to sigma divided by omega epsilon. To characterize different materials, we have already observed this one. So directly observe this equation, sigma which is given for us, omega, that what we have to calculate from F, epsilon is also given to us. So a direct substitution is enough here, that which is equals to 1.7 multiplied with 10 power minus 4 divided by omega is 2 pi f. So 2 pi into f is 3 gigahertz, that is 3 into 10 power 9 multiplied with epsilon. Instead of epsilon, what we have to write? 78 epsilon naught. That 78 into, here what I am doing is I am taking the epsilon naught value in different form. The actual form that what we have is 8.854 into 10 power minus 12. Instead of that one, we can take another one, that is 1 by 36 pi into 10 power minus 9. So here clearly 10 power 9, 10 power minus 9 will be cancelled. This 2 pi will be cancelled with this with 18. So 18 goes up, divided by 78 is multiplied with 1.7. Approximately the answer what we get is 1.3 into 10 power minus 5. So the loss tangent is very less. That means there is very less loss in this particular medium. So the wave can travel for a very long distance without attenuation. That you can observe the same thing with the help of sigma also. So don't go for any calculation blindly. We can say with the help of sigma like this. Whenever the sigma is very less, the loss tangent will be very less. The conductivity is less, corresponds to less loss. Less loss corresponds to more depth of penetration, that a wave can travel for very long distance. So the option is 1.3 into 10 power minus 5, that is option A is right for this problem. A material has conductivity of 10 power minus 2 mole per meter and a relative permittivity of 4. The frequency at which the conduction current in the medium is equals to the displacement current. Options are given like this. Option A 45 megahertz, option B 90 megahertz, option C 450 megahertz, and option D 900 megahertz. Here clearly for a particular medium, that sigma is given to us, sigma equals to 10 power minus 2 mole per meter, and relative permittivity is given to us epsilon r is equals to 4. Here the basic condition here is the conduction current is equals to displacement current. We must calculate at which frequency these two are equal. That what we are supposed to calculate. So whenever we are saying that the current is equal, the current density is also equal. So whenever we write conduction current is equals to displacement current, the same can be taken as conduction current density is equals to displacement current density. That what I am using here. So for this, clearly consider the conduction current density JC is equals to displacement current density ZD. Just what I am doing is I am taking the magnitudes of them. So magnitude of JC is equals to magnitude of ZD. And recollect the fields in our materials. In that one we got the JC equation. JC is equals to sigma multiplied with E, which is equals to ZD. This displacement current is observed at Ampere's law, that whenever there is some inconsistency in Ampere's law, the Maxwell added this displacement current. That what we got as dou d by dou t. That dou d by dou t can be replaced with j omega d in our point form, right? Here I am considering that one, that dou d can be replaced with j omega and d. So here this j omega d is nothing but the displacement current density. This j omega is the replacement of our dou d by dou t, and this d can be written as epsilon e. So which is equals to omega epsilon e, that what I am writing. That's since I am considering only magnitude, this j can be ignored. Now E will be cancelled, so sigma is equals to omega epsilon. What we require is the frequency, so write down this omega as 2 pi f epsilon. So f is equals to, clearly f is equals to sigma by 2 pi epsilon, which is nothing but sigma divided by 2 pi. Epsilon can be written as epsilon naught epsilon r. So 2 pi epsilon naught epsilon r is 4. That's what I am writing. So f is equals to, instead of sigma, what I am writing? 10 power minus 2. 10 power minus 2 divided by 2 pi into 1 by 36 pi into 10 power minus 9 multiplied with 4. After simplification, what we get is just 45 megahertz. Just to simplify them, then what we get is 45 megahertz, and the option A is correct here. So clearly calculate this one using a normal calculator. So option A, 45 megahertz, that what we have is the answer. A uniform plane electromagnetic wave incident on a plane surface of a dielectric material is reflected with a VSWR of 3. What is the percentage of incident power that is reflected? The options are given like this. Option A 10%, option B 25%, option C 50%, and option D is 75%. So here clearly a wave is traveling and it is taking some reflection. Here instead of giving reflection coefficient, what he is giving is the VSWR, voltage standing wave ratio. That clearly we have a relation between the VSWR and reflection coefficient. What is the relation between them? This VSWR is denoted with symbol S. S is equals to 1 plus magnitude of gamma divided by 1 minus magnitude of gamma, where gamma is the reflection coefficient. Simply it is given as 3. So 1 plus gamma divided by 1 minus gamma is equals to 3, corresponds to, with a simple analysis, directly we can say that gamma is equals to 1 by 2. That whenever 100% of electric field is incidenting, then half of that one is the reflecting, right? Reflection coefficient is nothing but that simple reflection power, how much it is reflecting, that what we require. But don't think that which is our answer. Here what he is asking is power reflecting, it's not incident field reflecting. That the reflection coefficient is always defined as gamma is equals to ER divided by EI. How much electric field will be reflected when some electric field is incident. Now we are supposed to convert this one into the power notation. So what is the relation between power and electric field? That clearly we have a relation between power and electric field. Power is directly proportional to E square. So whatever the equation we consider, the average power or the total power, directly it is proportional to the E square. So here what we have to do is, we need to consider that PR divided by PI, which is equals to ER square divided by EI square. The proportionality constant that what we have like characteristic impedance will be cancelled here. So ER square divided by EI square, which corresponds to ER by EI whole square, which is equals to gamma square. Now what is gamma here? 1 by 2. 1 by 2 square is nothing but 1 by 4. So clearly PR by PI is equals to 1 by 4. That corresponds to power reflected is equals to 1 by 4 times of PI. That is 25% of incident power. That what we can say. So whenever power is incidenting, some power is incidenting on the power reflected is 25% of the incident power. So option B, that what we have in our options is correct. That is 25% of the incident power will be reflected. This is a simple question that directly by considering the relation between VSWR and reflection coefficient, we can get this answer. Two coaxial cables 1 and 2 are filled with different dielectric constants epsilon r1 and epsilon r2 respectively. The ratio of wavelengths in the cables are option A under root of epsilon r1 by epsilon r2, option B under root of epsilon r2 by epsilon r1, option C epsilon r1 by epsilon r2, and option D is epsilon r2 by epsilon r1. Here clearly the data which is given to us is like this. Optical fiber cable 1 is filled with some dielectric material with constant epsilon r1, The optical fiber cable 2 was filled with some other dielectric material with dielectric constant epsilon R2. We require the ratio of wavelengths which is traveling in these two optical fiber cables. So what we have to do is to calculate this one, we require what is the basic equation of our wavelength. What is the basic equation of wavelength? Lambda is equals to, it is the ratio of 2 pi by beta. Just it is 2 pi by beta always gives us a lambda, right? So what is the equation of beta? From our wave propagation, beta is directly can be written as 2 pi divided by omega under root mu epsilon. And identify here, the filled material is a dielectric material. Since it is a dielectric material, it can be treated as a non-magnetic material. For non-magnetic material, this mu is fixed and it is equals to mu naught. So clearly with this equation, you can say that lambda is inversely proportional to under root of epsilon. Since this 2 pi is constant, omega is constant, mu is constant, we can take a simple relation that lambda is directly proportional to 1 by under root epsilon. So clearly with this equation we can solve this problem. Lambda 1 by lambda 2 which is equals to 1 by under root epsilon 1 divided by 1 by under root epsilon 2, which gives directly under root of epsilon 2 divided by epsilon 1 here. So lambda 1 by lambda 2 is equals to under root of epsilon 2 by epsilon 1. Epsilon 2 can be written as epsilon naught epsilon r2. Epsilon 1 can be written as epsilon naught epsilon r1. So epsilon naught will be cancelled and the quantity which remains for us is epsilon r2 divided by epsilon r1. So this is simply option B. So for this problem, just what we have to do is, we need to observe what is the basic equation of lambda, and here we got beta, and we have to write down the equivalent of beta in what we got in our wave propagation. Since it is a lossless medium, beta can be taken as omega under root mu epsilon. So option B is right for this problem. A plane wave propagating through a medium, epsilon r is equals to 8, mu r is equals to 2 and sigma equals to 0, has its electric field given by E equals to 0.5 e power minus z by 3 sin 10 power 8 t minus beta z volt per meter. The wave impedance in ohms is option A 377, option B 198.5 angle 180 degrees, option C 182.9 angle 14 degrees and option D is given as 188.4. For a given dielectric medium, the data was given like this: epsilon r is equals to 8, mu r is equals to 2, sigma equals to 0. Some electric field equation is given to us, right? Just you interpret the data first. That epsilon r equals to 8, mu r equals to 2 corresponds to, it is not a non-magnetic medium, that may be some magnetic medium. But here sigma is equals to 0, it is not a conducting medium, right? Sigma equals to 0 also corresponds to the attenuation of the given material is simply 0, it is a lossless medium. The electric field is given to us, right? We are supposed to calculate the wave impedance. What is the basic equation of wave impedance? Just recollect the basic equation of wave impedance, eta. So eta is equals to under root of j omega mu divided by sigma plus j omega epsilon. Since sigma is equals to 0, j omega mu divided by j omega epsilon we get. J omega will be cancelled. That directly it will be equals to under root mu by epsilon, right? This mu can be replaced with mu naught into mu r. Epsilon can be replaced with epsilon naught into epsilon r. That what I am doing here. So which is equals to mu naught and mu r is given as 2 divided by epsilon naught, epsilon r is given as 8. So under root of mu naught by epsilon naught, this is a very much known constant to us, that is nothing but the intrinsic impedance of our free space, which is equals to, directly you can write this one as 120 pi multiplied with under root of 2 by 8 is nothing but 1 by 4, right? So 1 by 4 is in square root, which is equals to 1 by 2. So which is simply 60 pi. So approximately equals to 188.4 ohms. So the wave impedance for a given medium, particular medium, can be calculated in easiest way like this. So this option is available, this answer is available in option D. So option D is right for this particular problem. An elliptically polarized wave traveling in positive z direction in air has x and y components as Ex is equals to 3 sin omega t minus beta z volt per meter, dy is equals to 6 sin omega t minus beta z plus 90 degrees volt per meter. If the characteristic impedance of the air is 360 ohms, the average power per unit area conveyed by the wave is. Options are given like this. Option A 31.25 watt per meter square, option B 62.5 watt per meter square, option C 125 watt per meter square, and option D is 250 watt per meter square. Here clearly a wave is traveling in a particular medium, and the characteristics of that particular wave, that is the components of wave in x direction and y direction, are given like this: 3 sin omega t minus beta z. Here it is 6 sin omega t minus beta z plus 90. Just leave the data and examine these two components. These two components have two different amplitudes. X has 3 amplitude and y has 6 amplitude. And if you observe, the phase difference between these two is 90 degrees. So different amplitudes, 90 degrees phase difference always corresponds to elliptically polarized signal. That what is given in our data. And then we are supposed to imagine that the characteristic impedance of the medium as 360 ohms, right? We need to calculate the average power density. Here once again it is average power density. Since it is power density, watt per meter square, power per area we are supposed to calculate. That can be calculated using our Poynting vector. The Poynting vector is just 1 by 2 E cross H. But here what we are calculating is only the magnitude, right? So directly we can write that one as 1 by 2 E multiplied with the magnitude of our H. Directly I am taking that one. So power average PAVG is equals to 1 by 2 magnitude of E magnitude of H. So once again observe here, in this equation we have no H. So directly we are supposed to convert this H into E. This is very much known to us. H can be converted to the component of E like this. E by eta can be directly taken as H. Here we are taking a free space medium. E by eta naught we are supposed to consider, which is equals to 1 by 2 magnitude of E by eta naught. So E square by eta naught, which is multiplied with 1 by 2 will gives us the answer, right? Now eta naught is equals to 360. Then what about this E square? Just to take the magnitude of E square or the E from this Ex and Ey. So I am taking this magnitude of E is equals to under root of Ex square plus Ey square, which is equals to Ex square is nothing but 3 square plus Ey square is 6 square. So 36 plus 9, which is equals to under root of 45. Now directly the average power can be P average is equals to 1 by 2 E square is 45 divided by eta naught. Eta naught is 360. So approximately after calculation of this one, what we get is 125 divided by 2, which is equals to 62.5 watt per meter square. So clearly the average power, always remember that the average power can be calculated with the help of our Poynting vector, that is 1 by 2 E cross H, or if you are considering the magnitude, just it is 1 by 2 E multiplied with the magnitude of H. Directly the answer is 62.5 watt per meter square. This is available in option B. So option B is right for this problem. The electric field of a wave propagating through a lossless medium, mu naught and 81 epsilon naught are the characteristics of that medium, is E is equals to 10 cos 6 pi into 10 power 8 t minus beta x ay volt per meter. What is the phase constant beta of the wave? The options are given like this. Option A 2 pi radian per meter, option B 9 pi radian per meter, option C 18 pi radian per meter, and option D is 81 radian per meter. So these are the options given to us. Solution. For a wave or for a medium, clearly the characteristics are given like this: mu is equals to mu naught and epsilon is equals to 81 epsilon naught, and the electric field intensity equation is given to us. We are supposed to calculate the phase constant beta, right? Just examine this equation. This equation has omega here. That from the equation directly we can write omega is equals to 6 pi into 10 power 8. That omega is the angular frequency which is given as 6 pi into 10 power 8, and we require this beta. Epsilon is equals to 81 epsilon naught is given to us, mu is equals to mu naught is given to us. Since we have different values of mu and epsilon, it is not free space. Remember that point, that we are supposed to calculate some more parameters to get our beta. Now how to get beta from this omega and the quantities that what we have? Let us recollect the equations that what we have, that a phase velocity we have, that phase velocity is equals to omega by beta. That whenever you have calculated this phase velocity, directly you can obtain this beta. So beta is equals to, so omega by phase velocity. How we can calculate this phase velocity? We have a very good equation for this phase velocity as 1 by under root mu epsilon. So I will consider that one here. So phase velocity is equals to 1 by under root mu epsilon. That mu is equals to mu naught, epsilon is equals to 81 epsilon naught. That 1 by under root mu naught 81 epsilon naught, which is equals to 1 by 9 times of 1 by under root mu naught epsilon naught. What is 1 by under root mu naught epsilon naught? That is the constant, it's the velocity of our light. The velocity of light is 3 into 10 power 8 meter per second. So we got phase velocity, and from the problem omega is known to us. So just a direct substitution will give us the answer. Beta is equals to omega. Omega is 6 pi into 10 power 8 divided by, our phase velocity is 1 by 9 into 3 into 10 power 8. Direct substitution of our omega and phase velocity will give us the answer. So beta is equals to omega by phase velocity. Omega is 6 pi into 10 power 8 divided by the phase velocity is 1 by 9 into 3 into 10 power 8. The 10 power 8 will be cancelled. This 3 goes 3 times here. So this 3 goes upwards. Then 3 into 6 pi, which is equals to 18 pi radian per meter. So this will be the answer. Just a very simple one. What we have to do is we have to observe what are the parameters which are existing that in our given problem, and how we have to wisely use them. That phase velocity is equals to omega by beta is a very important equation in this one. This 18 pi is coinciding with our option C. So for this problem, option C is correct one. The electric field intensity in free space is E equals to 12 cos 5 into 10 power 8 t minus beta z ax volt per meter. The time period of wave will be dash. Here the electric field intensity equation is given to us. The electric field intensity equation E is equals to 12 cos omega t, that here the omega value is given to us, minus beta z ax volt per meter. Clearly it is traveling in positive z direction and it has a component in x direction. We require time period, a very simple one. Just consider this omega, nothing more than that. What we have is omega equals to 2 pi f. So angular frequency is equals to 2 pi f. This f can be brought out and that can be written as 1 by f is equals to this 2 pi by omega. That this f was come this side and this omega was brought to right hand side. That 1 by f is nothing but simply time period. Time period t is equals to 2 pi divided by, what is omega here? Omega is equals to 5 into 10 power 8. That 5 into 10 power 8 I am considering here. Direct substitution, nothing more than that. Take this omega and substitute here. Take the equivalent of this omega, which gives us 2 into 3 approximately 6. 6 divided by 5, 12. 12 into 10 power 8. That is simply it is 1.2. 1.2 into 10 power minus 8 second. So this will be the answer, but don't leave this one. Sometimes this will be given an approximated one, that here this may be written in terms of nanoseconds. If you want to write down this one in terms of our nanoseconds, simply it will be equals to 12 nanoseconds. So this will be the answer, a very simple one. Interpretation of data, nothing more than that. So this is a simple solution. In free space, E equals to 50 cos omega t minus beta z ax volt per meter, and H is equals to 5 by 12 pi cos omega t minus beta z ay ampere per meter. The average power crossing a circular area of radius square root of 24 meter in plane z is equals to constant is. Here in this problem, clearly observe what is the data given to us. The data given to us is the electric field intensity E is equals to 50 cos omega t minus beta z, which is in the direction of x, and H is equals to 5 by 12 pi cos omega t minus beta z ay, and clearly it is traveling in free space. At the radius of circle, that what we are considering, or the radius of the area is the square root of 24 meter. We are supposed to calculate the power. Here clearly remember, it is not power density, it is power. That what we require is the power that can be obtained from power density. So initially if you obtain the power density, multiply that power density with the area that what we require, then that gives the simple power. So the basic equation can be written as power is equals to power density, that PD stands for power density, multiplied with area, that where we are considering that particular power density. How we can calculate this power density? This power density can be easily calculated using our Poynting vector, that the average power density is 1 by 2 magnitude of E magnitude of H. So the magnitude of E, directly take the magnitude of A is 50, nothing more than that. The remaining entire term is just for wave phenomena, right? Magnitude of H is 5 by 12 pi. So which is equals to, directly I am writing here, 1 by 2 multiplied with the magnitude of E is 50, and the magnitude of H, directly I am taking this one as 5 by 12 pi. That what I am considering. And what is the area of particular region what we are considering? Here a circular region we are considering, and it has some radius under root 24. So what is the area of the circular region we are considering? Pi r square, pi into radius square. So I am writing directly pi into radius square. Radius is under root 24 square. So clearly identify this quantity, that what I am writing is the area in which we are calculating the power, which is multiplied with the power density. Just you simplify this one, pi will be cancelled. 12 into 2 is 24, this is 24, 24 into 24 will be cancelled, 5 into 5 just 250. That is the answer. But what are the units? We are calculating power, we are not calculating power density. So clearly the units are watts. So 250 watts is the answer. So in the options, if there are any options, definitely he will give watt per meter square as one of the options. 250 watt per meter square, 250 watt, or 125 watt, 125 watt per meter square, like that he will give some options, but clearly identify that the power we are calculating will have units only watts. This is a very simple solution. 3 different dielectrics of permittivities 4 epsilon naught, 9 epsilon naught and 3 epsilon naught are defined in the space as shown below. That is, the figure is given here. If leading edge of the uniform plane wave propagating in x direction is incident on the plane x is equals to minus 6 meter, then how much time it will take to strike the interface defined by dielectric 2 and dielectric 3? Here clearly observe what is the solution. Before that, just interpret the data which is given to us. A plane wave is propagating and it is striking at some x is equals to minus 6. And it is continuously it is traveling in this forward direction, right? While it is taking the propagation, it is crossing different mediums. Initially it is going from free space, and later it is entering some dielectric medium. After that it is entering some other dielectric medium, and finally it is going to the space with last dielectric medium. Like the different dielectric mediums are given to us. We are supposed to calculate how much time it will take to reach this interface whenever it hits the medium at x is equals to minus 6. That we are supposed to calculate the total time taken by the wave to reach this interface, right? This is a simple problem if you understand it properly. How you can calculate the time with the help of distance and velocity? Directly we have a relation. Time is equals to distance by velocity. Clearly here the distance factor is given to us. That this is one distance, this is next distance, this is the third distance. So what I do is I will take the total time taken to travel up to this part as the distance d1. Let us take this is distance d1. In this particular region, let us take the velocity is v1. Later it is traveling in this with distance d2 with velocity v2. Since it is another dielectric medium, we are supposed to consider another velocity. And in the third one, let us take the distance between these two is d3 and velocity is v3. So if we have those distances and velocities, easily you can calculate the time. So here I am writing the total time taken, t is equals to the distance by velocity in the first medium, d1 by v1, plus the distance in the second medium, that is d2 by v2, plus in the third medium it is d3 by v3. Just observe, in the first medium it is traveling from -6 to 0. So the total distance traveled is 6 meter. In the second medium it is traveling from 0 to 3. So the total distance traveled is 3 meter. In the third medium it is traveling from 3 to 5. So the total distance traveling is 2 meter. Right? The distances are obtained. d1 is 6, d2 is 3 and d3 is 2. Now we are supposed to obtain the velocities. How to obtain the velocities? As we know, the velocity obtaining is very simple when we have this mu naught and epsilon naught. That's the phase velocity we are supposed to take. Here, what is the phase velocity? Phase velocity in this space is directly equals to the velocity of our light. So directly instead of this v1, you can write velocity of light, that is c. And the second one, velocity of our wave in the second medium, v2 can be calculated using simple formula 1 by under root mu epsilon. What is 1 by under root mu epsilon? Where mu is equals to mu naught, epsilon is equals to 4 epsilon naught. So that's what I am substituting here, that 1 by under root mu naught 4 epsilon naught. Mu naught into 4 epsilon naught is nothing but just it is c by 2. 1 by under root mu naught epsilon naught is c, under root of 4 is 2, that is c by 2, that what we have as our velocity 2. And go to the velocity 3. In the velocity 3, that what we have is simply 1 by under root, once again it is mu naught, and instead of epsilon we are supposed to take 9 epsilon naught, that is 9 epsilon naught I am writing. So directly this can be written as c by 3. So here clearly just observe what I am doing. I am calculating the distances initially. I obtain the distances d1, d2, d3. Later I am calculating the velocities. Velocity is equals to c here, and here it is something we got as c by 2. Here in this region we got as c by 3. Substitute there. So the total time taken is equals to, here d1 from this point to this point is 6 meter divided by velocity is c. So just d divided by c, 6 divided by c, plus d2. d2 is from 0 to 3. From 0 to 3 how much we have? Just 3 meter divided by the velocity is c by 2. That c by 2 will be written here, plus the third distance from 3 to 5. 3 to 5 the distance is just 2 meter divided by the velocity is c by 3. That c by 3 we have. So 6 by c plus 3 divided by c by 2 plus 2 divided by c by 3, which is equals to 6 plus 6, 18 divided by c. That's what we have. Just directly substitute c there, which is nothing but 18 divided by 3 into 10 power 8 meter per second. That's what I am substituting there. This 3 goes for 6 times, which is equals to 6 into 10 power minus 8, which is nothing but 60 nanoseconds. So clearly here observe what I am doing. The total time taken to propagate the wave or to travel the wave from this location to this location I am calculating. That since it is traveling from different medium, I will calculate the different time taking with the help of the distance traveled and the velocity in that particular medium. The most important equation that what you have to remember is this equation, that 1 by under root mu epsilon. If you have that equation, easily you can calculate this one. So the answer is 60 nanoseconds. So these are some of the problems that what we have in our wave propagation. Like this we can solve many number of problems using our basic concepts what we learnt in our wave propagation.